So I have been talking about this problem which is called variational quantum eigensolver, and it is specific to studying the low-lying states of many fermion systems. Okay. There is a review article which is a good reference, and it's available on archive. Okay. So what is the structure which is used is there are essentially a set of problems, mostly from quantum chemistry, involving n electrons, and their states are constructed out of capital N orbitals, and for every electron there is a location and a set of orbital for that particular location. So I gave one example where the basis which was used is this STO3G, and it had 3 orbitals for every electron. The job is to find a superposition among this finite number of orbitals for every electron, which gives the lowest energy. And of course, you have multiple possibilities for every electron, so the total state in the whole superposed description will be an entangled state. Whatever it is, it's a complicated wave function, and the emphasis is on calculating the energy accurately without worrying too much about the wave function. So that is because of the nice property of the variational methods that energy is always found much more accurately than the accuracy of the wave function. But you can't turn it the other way around, that you found good energy value. It doesn't mean that you have found a good wave function. You have to work harder. In particular, you have to develop alternative estimates of how good the wave function is. One possibility is to calculate the variance of the Hamiltonian, and if you have an exact eigenstate, the variance will go to 0, but if the variance is large, that means our wave function is not very good. Okay. So all those caveats are present, and the Hamiltonian has one particle and 2 particle terms. Nothing more than that. And that one particle term is, for example, covers the kinetic energy and sort of mean field description. Two particle term can cover Coulomb-Coulomb interaction between two electrons, but nothing more than that is contained in the Hamiltonian, which means that the number of possible terms, whatever appears, is finite. It can be written in the second quantized notation. So one particle terms will have structure A dagger A for that particular location, and two particle terms will have A dagger A in one location and A dagger A in the other location, and then many permutations of that. And for that reason, since we are going to label A dagger and A belonging to this n orbitals depending on what is occupied and what is unoccupied, so the total number of Hamiltonian terms generically described using the Pauli basis is order n raised to 4. A dagger and A can be acting on any one of these n orbitals, and you have two body interactions which have 4 factors of A dagger A, and so this counting can go all the way up to order n raised to 4. And I gave a simple example of the Jordan-Wigner encoding in the previous lecture, which illustrated how these various terms appear. But there is one more quantification which is used, and that is number of Pauli operators in individual term of the Hamiltonian. So there are so many terms, but since the interactions are only one body and two body terms, when you write down, they will have only Pauli matrices in some location, all the other stuff will be identity. And that requires a different label, and it is called Pauli weight of the operator. How many of this product of various Pauli basis terms have matrices which are different from identity. So if you have a two-body interaction, only those two locations will have matrices different from identity. Everywhere else, all the other n minus 2 electrons, whatever factors are there, are equal to identity. And this plays a very important role, because when you want to calculate the expectation value, these operators will have some Pauli matrices at that location. Rest of the wave function will have only identity terms, so it is like taking a trace of a reduced density matrix. Those things don't play any role as far as whatever circuit or gates you want to construct to measure the operator of H. And so the effort required to make an individual measurement is actually limited to Pauli weight, and then you have to collect so many different terms and add all of them together. So So if you reduce the Pauli weight of the operators, work can be brought down. What is also true is that the Pauli basis, the operator you will measure, they will have only individual reading of +1 or -1, because whatever operator you choose is Pauli basis, eigenvalues are all +1 and -1, and then you have to run the algorithm many times, perform measurement of how many times it is +1 and how many times it is -1, and then put them together to calculate the expectation value. So it's and how accurately you need to do this, that we went through the exercise earlier in a different context, that you have to use Chernoff bound to get the expectation value of this ±1 measurement within a particular range, and then you will have an answer. So and the important property of the Chernoff bound was that number of measurement basically scaled as log of 1 over epsilon. Okay. So you have to do this all one by one, and then you add up everything and you have an expectation value of the Hamiltonian. Now the job is not done. So then there is a hybrid technique that you find H for some specific values of the parameters. Those are all variational parameters, and they include, for example, nuclear coordinates. What are the physical locations of the n electrons which you are distributing, and certainly these interaction strengths, whatever they are, the Coulomb part, etc., they depend on the positions of where the nuclei are, because orbitals are centered on individual nuclei, and these other parameters are these superposition positions for the excitations. For example, here I took 3 orbitals for 1 electron, and it is some combination of the various superposition coefficients for those 3 values, and they are variational parameters. And you need to find them, because that is what completes the and then the tougher part is to now minimize it as a function of all these various parameters. So how do you do that? Well, the quantum theory doesn't help you there. You calculate various discrete set of choices of the parameters, compare them, find a gradient, move in that particular direction until you reach the minimum. So it's a complicated multidimensional exercise, and that is essentially done with a classical optimization. So as you can see, it's a complicated job. You start with whole set of terms in the Hamiltonian, calculate each one of them one by one, add them together till you have a sufficient accuracy, and then change the parameters, do the same thing again, change the parameters, do the same thing again, compare all the various results, and then you find some local minimum, and it requires a good amount of work, and that actually limits how large systems you can simulate. Okay, so at the moment, the methods have been implemented on just the classical computers, or even if you want to do it in the quantum algorithm with a simulator, which is just converts the Pauli matrices into linear algebra and does the same job. But the status is that computational capability how much you can handle. Well, this n, which is essentially the size of everything, it is order 10. Rather limited. You can't say that I will go one more order. Can I do n equal to 100? No way. Going from even 10 to 20 will be a tough job. Okay. So that is because of all these things you have to put together, and it's a rather complicated exercise and takes time. And the question comes, well, if this is the case, how much you can study, and the applications of quantum chemistry for that reason are limited to rather small molecules, 2 atoms, 3 atoms, something like that. But the point is that even for those 2 atom, 3 atom cases, the conventional information which is there in chemistry textbooks is not good enough. Okay. And so if you can find a sufficiently good description of energy as well as some estimate of the wave function, it can be useful. Okay. And The examples are kind of very simple. The simplest thing is just a hydrogen molecule. Okay, you solve single hydrogen atom exactly using Schrodinger equation, but even the next step, what is the chemical structure or the electronic wave function of the hydrogen molecule? Well, we don't know too much about it. You know that it forms a bond, and experimentally the values are very well measured, but how well you can reproduce it, that is a different story. And if you find an application which can explain the the dynamical wave function which is there for a hydrogen molecule, it will give a good deal of knowledge beyond what is there in the chemistry textbooks. And then you can produce many things, and people have tried out again small molecules which are experimentally accessible, and they are simple dielectric molecules like lithium hydride. Experimentally you can observe it. It's a 2-atom molecule, but while this one is symmetric, this is asymmetric. So you have to now study the orbital, how much is on the lithium side, how much is on the hydrogen side, find an estimate of it and calculate its property. It will have a dipole moment, for example, because the charges on the two ends are different. And you can make some understanding of a very simple bond between these two molecules. Then there are very simple examples again where we don't know very much about it because of unusual properties. Another diatomic molecules of interest is carbon monoxide. And it's a kind of peculiar because in many of the chemical textbooks you'll find that oxygen becomes a negatively charged ion, and whatever the metal part will have a positive charge of ion. But if you now look at this thing experimentally, where is the negative charge and where is the positive charge? It's the opposite. Oxygen has a positive charge and carbon has a negative charge. Can you understand it? Well, it's a tough exercise. The chemical rules don't give you very much idea, but yes, it's experimentally accessible. Now you make a good model of it which can give a description. Then, well, these are all very simple things. Well, together with carbon dioxide, there is a carbon dioxide, another molecule little bit bigger, but now the structure is that all these things had a single bond, this one has a double bond. The carbon has 4 electrons, 2 are bound to one oxygen, the other 2 are bound to another oxygen. Well, what is the structure of the double bond? It's going to be a different description than the single bond orbitals, how well you can understand it. Another important molecule is water. 3 atoms like carbon dioxide, but while this one is a linear molecule, this one is bent. So another geometry to understand why it is bent and how the wave function is related to it, and understand it in some level. Yeah, one more I can label is ammonia, which is again a something which is a little bit extended structure. It actually like a pyramid. The 3 hydrogen are equivalent, but the nitrogen is not in the same plane. It is above. And then there is a resonance that compared to the hydrogen plane, whether the nitrogen is above or whether it is below, and it can tunnel in the 2 locations and give all kind of effects due to that. And we can study it experimentally very well, but theoretical model is complicated enough. So these are the small molecules which have a lot of chemical structure, and they can be studied with something of this type. Well, 10 orbitals are there. You can study some 2 or 3 atoms reasonably okay, and all these methods have been applied to get a good estimate of that. The starting point is again not very good. As I said, most of the time the calculation uses this kind of Slater orbital with a Gaussian wave function. We know that with Coulomb interaction, the wave function are not Gaussian, they are exponential. So you just don't worry too much about it and try to get good energy description. But you want to do better when you have to improve your fundamental set from this orbital to some other better approximation and see whether you can get a more detailed understanding of the wave function, not just the energy. So these are all problems, and people have tried to simulate it, and they have, after all the classical simulation, they have tried to put it on a quantum simulator and see how well these things work. It's sort of good enough, but as I said, this how well you want to understand this. So this can be studied to what I had labeled earlier as chemical accuracy. You don't need to solve them to high precision like an exact solution. Even if you get an estimate of the properties to some chemical accuracy, essentially decided by the thermal fluctuations of the order of kT. And if you can get there, then you have a good understanding of how these molecules will get involved in various chemical reactions. So this is a exercise, and this is as far as people have progressed. Okay, so now where is the difference in the simulation between classical and quantum version, which is again something which I mentioned last time, so-called coupled that is an attempt to cover a range of the superposition coefficients as function of various parameters. What it does is a cluster operation that you have a final state which you want to estimate, and it is created as some excitation operator acting on the initial ansatz. Initial ansatz can be something from this wave function. Many times it is obtained using what is called the Hartree-Fock method. Some starting point, and then what this does is includes, so this A are variational parameters. It's actually it's a whole set. So, and there is a whole set of T which are transition operators. Yeah, they are. Want to write this a whole sum over all possible things. So, from the ansatz, you can create a transition operator which will take you from one orbital out of this set to the next orbital, and then corresponding strength is this variational parameters, and this is a huge operator. There is I could have written just a ordinary power series instead of an exponential, but the reason for using the exponential form that it has properties which chemistry people keep on emphasizing. It is, well, these are the two labels which are used. Extensive means that as you add more and more number of orbitals, how fast this complication of evaluation grow, it is basically proportional to the number of orbitals like n, and this form kind of guarantees that. Size consistent means the parameters like this nuclear coordinates, what happens when you make the separation large, then you should have the molecule which dissociates without going into any other random state. It's like you take hydrogen, increase the nuclear separation, it should give you 2 hydrogen atoms and not something else, like not one proton and the other one in H minus, and that doesn't happen. So nice properties like that are called size consistent, and the exponential form kind of guarantees that, and that is why it is used. And there is another way to interpret it as this property, how they come from. If I want to calculate, not this H, yeah, the expectation value of the Hamiltonian in this new state, that is what I am doing all the time. So this is equivalent to calculating a different Hamiltonian in this initial ansatz. To understand this, it's actually nothing but substitution of this, but why the negative sign comes over here has to do with the fact that how do this operator transform. This, once you take on the opposite adjoint state, you have to construct the conjugate of this particular operator, and that conjugate actually flips the sign over here. It has to do with all the anti-commutation rules which are sitting inside this operator. The transition operators will have a dagger and a, and when you take a conjugate, well, those things flip around in sign, etc. You just have to follow it through, but the result is it gives this nice structure, and this is what is well known in linear algebra. It is called a similarity transformation, and if you want to explicitly evaluate it, it will end up with calculation of commutators of H and T. There is no time dependence anywhere. These are all static problems. However many excitations you want to include. So this fact that what you are doing with this excitation is essentially a similarity transformation that is guaranteed by the exponential form, and then you can expand it in terms of commutators if you want such behavior. But the point is that this structure guarantees various properties connected with normalization, and you don't have to worry about the normalizations getting spoiled. And that is why it is written generically in this coupled cluster theory, some exponential excitation operator. And all that is done, the quantum version of this coupled cluster theory is, this exponential is there, you make it unitary. And after that it is same exercise going all over again, trying to find all the coefficients, etc. But unitarity is easily guaranteed by replacing this e raised to some a, I will just write a t to e raised to I a dotted with t minus t dagger. Okay, this I is not needed because this is t minus t dagger is already anti-Hermitian. So the exponential structure is preserved, and on top of that, here it was a similarity transformation. The norm actually of this operator is not necessarily 1, but in this form the norm is guaranteed to be 1, and it's little bit different looking thing, but it can cover the same structure, that it will create all kind of excitations. And so you vary the parameters buried inside here again and search for a minimization solution for the energy. So that is the game, and all the algorithms. Now probably there are some ready-made packages also probably available on Qiskit, things like that. You specify a number of orbitals, specify the number of transitions, and then it will perform these operations on the state and give you some answers. The minimization, this classical part, is a tough job that you have to do it by a different technique. The whatever algorithms in the library like Qiskit, they will not do that job for you. Okay. So after this, now there are various tricks which are all various kind of simplifications which can be constructed on this overall structure. And these are tricks people have just played around with them by trial and error kind of thing, trying to see if you can cut down the job, and then the calculation becomes simpler, and whatever you can get is useful. So where can the simplifications occur? And there are various possibilities. I will give the justification, but yeah, okay. First, what the simplifications do? So reduce number of terms in the Hamiltonian. This n raised to 4 is too large. Can you bring it down? And the answer is yes, you can do a reasonable job. Where you make full use of symmetries and the interaction range. Symmetries can exist in the system. For example, in hydrogen molecule, the two atoms, whatever they are there, they are equivalent, and you don't want to do everything. There will be double counting. Get rid of that double counting. What does interaction range offer? That the molecules have a geometry in a three-dimensional space, and most of the interactions are all local, nearest neighbor kind of stuff. They don't go all over the place. If you assume that, then also the number of terms which go down, because all these orbitals are not going to interact with something which is arbitrarily far away. It will interact only with its neighbors. And if you do that many times, you can bring down this number. So the change can be rather drastic. n raised to 4 can be come down to n square. Why n square? Because it is still a two-particle interaction. I can't get rid of that. So n in one location and n in another location can give you two-particle interaction. It can't be brought below that, but if you can get down these terms to this, it can help quite a lot. And what you have to keep track of is that, yes, all these operators are there. The number of possible terms in the Hilbert space is n raised to 4, but most of them are not going to appear in this, so you just relabel them. And what you call sigma x, sigma y, sigma z, it doesn't matter. All you need to maintain is the polymetrics commutation rules. You can call it sigma x by any other operator, doesn't matter, as long as the commutation rules are satisfied, and then you cut down essentially all the labels which had an identity factor. And you relabel everything so it is all in the smaller space. The rest of the stuff is identity, it's not going to do anything in the calculation, you truncate.
So relabel means we are changing the notation of polymetrics.
You can relabel it any way you want as long as the commutation rules are satisfied. That is all that will matter for the calculation. So you juggle around all the labels, whichever one comes first, second, it doesn't matter. Job is to basically compress the whole set of labels into a smaller space, and then all the identity factors, you just remove the corresponding qubit labels which are associated with them. They are not going to play any part in the calculation. So this is something which is possible, and there is a well-known example which was last year illustrated on a Q-skit problem. That is what is called there is some particular geometry which is called Kagome star. So it's basically a truncated hexagon, which if you count the number of points, it has 12 points. 12 for the corners of triangles and 12 for the, or 6 for the corners and 6 for the inside hexagon. So the job was to, this was one of the Q-skit challenge problem, and to model this and find the ground state energy for a antiferromagnet put onto this particular lattice. So the number of qubits was reduced from 12 location to just 5. You didn't throw out any, you did not delete any of the terms of the Hamiltonian, but you had a knowledge that the interactions are nearest neighbor. all the terms were not there, and there you just relabel everything in some clever manner for nearest neighbor. Yeah. And looks like a small factor, whatever it is, as far as number of qubits is concerned, but it makes a hell of a difference whether you can simulate it effectively or not, given the status of our computational capabilities, both in the classical domain and the quantum domain. So this is one simplification which occurs and which is useful. The other simplification which is also useful is reduce what is called depth of it's not dividing is not the right word. That still there are large number of terms which will there in the Hamiltonian. It came down to some extent, but there are a bunch of operators. Now, whatever those operators are, they are all still going to be in the Pauli basis. And the important property for this particular task is that you write down all the Pauli basis elements involving sigma x, sigma y, sigma z, and either they will commute or they will anti-commute. There is no third option. Okay, so you look at that whole list, which may look complicated by the time you went through this, but then you ask which one are mutually commuting. And the advantage of mutually commuting operator is they can be measured simultaneously. So you measure all of them in parallel. And what is called the depth of computation, how many steps you have to do one after the other, that goes down. Okay. And how to do this efficiently? It's still a sort of open problem. For the small structures which are involved in here, you can just look at those things by inspection one by one and find that this commutes and this doesn't commute. You do it by hand and that is as good as anything else. But if you want to do some kind of automated algorithm, which for any given Hamiltonian figure out what are the mutually commuting sets, that is something which people are still playing with, trying to find the best way to figure out how this separation can be done. But it is possible, and when you do that, basically the computation time goes down, and that is important given all the current technology. The number of time steps before the quantum signal kind of gets destroyed is limited. So doing things in parallel is useful. You don't want the time to be very large, and that can be done. And there are various algorithms which have implemented these things in a certain sense. So that is another trick. And the best results for this, I will give you the answer that the depth is actually this Pauli weight of the operators, because when I mentioned this, I said that it tells you how many operators are different from identity. The identity part, don't have to worry about measuring it. Only the depth gives a non-trivial part, and you only measure those kind of things. And that is decided in the circuit, because when you are measuring certain product of Pauli operators, you have to have that many steps to collect the answers by the successive measurements collected into some ancilla, and that is the effort which is needed for measuring this just expectation value. And in the last lecture, I described the so-called Jordan-Wigner transformation, which is the easiest way of encoding. And it had a structure where you had a and A dagger at one particular stride, but to maintain anti-commutativity, you have to attach a whole string of factors of z on one side or the other, whatever you choose. And then if you now count the weight for that particular structure, so the Jordan-Wigner case, this weight is order n, because that is coming not from that A dagger and A at one particular location, but because of the string. You have to have all the product of operators from one end up to that particular location. And the possibility that this can be brought down, and that has been worked out thoroughly. And the gain is quite substantial. It can be brought down from n to log n. And that can help because it basically decides how many clock cycles you need to measure the expectation value. For the small numbers like 10 or 20, difference may not appear too large, but at least theoretically it's a clean enough advantage, and it can be done and explicitly demonstrated because this is a mathematical exercise. So I will give a simple illustration of how this is done, and details you can find in that particular article. So there are various alternatives, as I said here. Something which is easy to understand is parity encoding. So Jordan-Wigner case was the encoding in the occupation label structure of all the orbitals. And it was very direct, so physically easy to understand. Parity encoding is something which is related to it, requires a little bit of thought, but it's not too complicated. And what it does is it counts the orbitals in a particular sequence and asks the questions, how many orbitals before that particular locations are filled and how many are empty. And it has that for same information you go to the next step. If that orbital is empty, value increase the number by 0. If it is occupied, you increase the number by 1. And given one set of occupation label, you can construct it parity. So this I can give occupation label some new 1 to new n, and I can define the parity label which is 1 to 1 from this. And both of these are binary variables, only 0 and 1. Consequence of all the fermionic nature of the problem. So what is the parity value? Well, it just okay, J less than equal to I. It orders these orbitals in some sequence and counts how many below that level are filled. Okay. And the numbers are all zeros and 1 evaluated mod 2, and the inverse transformation is also quite straightforward. That what is the status of this? Well, I count how many from this location and how many from 1 minus that location, and the difference will tell me whether that particular label is occupied or not. So it's a straightforward label, nothing complicated, and then you can do the jugglery of what are the things or what are the operators going to look like in this structure. There is another so label for the matrix. If you want to go from one basis to another, so it will I will write this matrix. So I wrote everything below, so it will go like this. The diagonal one is the location, and when you do all the sum, it is adding all these numbers by transformation 1, 1, 1, except that at the end you do a mod 2 calculation. So, given a bunch of occupation label, applying this matrix will give you a parity label. And it's a straightforward enough definition, nothing more complicated. So now I can ask what is going to happen to this A dagger and A in this new representation. So the job of A dagger and A is the same. A dagger will create a particle at that particular location, A will annihilate. But the functions which are necessary to do that have to be now understood a little differently, because A dagger and A are not going to directly act on the parity label. So action of A dagger and A is on a state which is ordered in sets of qubits going from one end to the other. The whole thing requires a ordering. So orbitals are ordered in a sequence. You choose whatever sequence you want, but you have to make a sequence to be able to divide that. And now, what happens when I act with a dagger? Well, on this particular state, it's sitting somewhere, this is some index, I will put I. So you have to reach particular label there and then create an excitation or a de-excitation there. But before going there, you have to cross all the previous levels. And given this nature of these anti-commutation rules of A dagger and A, when you cross, if that level is occupied, the sign is flipped. If it is unoccupied, well, it doesn't matter at all. But you have to keep track of that, because now you have put a register in some sequence and the action of this thing is going to be on this. You have to keep on flipping signs. So what is the label now for this? So you can single particle. So the mapping, as I described last time, was at that particular site, I needed this xj and iyj by 2 operator, but I now, in addition to that, keep track of the sign, which will say whatever came before, whether it is occupied or not. And where is that information? Well, the information of occupation or not, you only need modulo 2, because 2 flips of sign will just get back to identity, nothing more than that, and that is precisely the parity variable. So what you need to do to this is multiply by z of the previous site. Why z? Because if the state is occupied, you have to flip the sign, that is the diagonal part of 1 and minus 1. The occupied value of z is minus 1. If it is not occupied, it is plus 1. And then this one has the same structure, except that this x and y parts are Hermitian conjugate. So this is what a single particle structure of this particular mapping is. Remember that now you are working on parity label, so if you have a parity value, some P1, it doesn't tell you what particles or whether that label is occupied or unoccupied. That you have to go back to the mu description, but you can directly perform a transformation with this particular label. That is essentially the job. And then many particle version, well, then I have to worry about what these operators will do in this parity basis. So took the action of here, you commutated all these operators up to that and changed something. But then the new state which has created the previous part, fine, it has been taken care of. But you created this something or annihilated at jth location, it means the remaining part of all the parities are flipped. Because if remaining part earlier was calculated assuming that this operator was not there, now you introduce one operator. So it flips the parity, not on the first part, but everything else the parity reverses. And what is the operator which allows me to flip the parity? Interchange 0 and 1, that is a sigma x operator. So now the single particle was this, the complete description looks like this. There is a z j minus 1 cross with So it's a different expression compared to the Jordan-Wigner case, but you end up with a string of operators from the location to one end or the other. So this problem of reducing the weight is not solved. It's still there. But yes, it's a simple enough exercise which tells you that there is nothing unique about ordering the operators in some particular way. You can transform the label by some invertible matrix, and that can give a completely different description. So the reason for giving both this Jordan-Wigner and the parity encoding is that individually this is also order n or another is also order n. But if you combine the two properly, you can bring it down to order log n. And this was a problem which was solved by Bravyi and Kitaev. It's a clever arrangement of things, but it's like half of it is this, another half is over this. This had a long string on one side, that had another long string on the other side. You merge the two, the string disappears. And that's something which needs to be worked out in detail if you want to understand. I will not provide all the details, but I will tell you the structure of how these things works. And so it's a kind of recursive method. Done in such a way that all the even labels follow the Jordan-Wigner label, and all the odd labels follow parity label. Some combination. And the easier way is to actually write down this analogous version of the transformation matrix, which will take you from the occupation basis to the Bravyi-Kitaev basis. And from there, you can work backwards and figure out what are the transformation on A dagger and A. So job is done in factors of 2 for this value of n. So it will go 1, 2, 4, 8, etc. and fill them up, and that is done so that you can calculate this explicitly with a log 2n. If n is not a power of 2, then you pad it up with some useless orbitals to make it an integer for the round off. So the way it is done is an implicit version, and so this matrix in the notation of this reference is for the size 2 raised to x. It is recursively defined as whatever it is for x minus 1. It is like a tensor product structure by adding labels, and this is very peculiar structure. Everything is 0 except for the last row, which is completely 1. And so you start with x equal to 0. The first matrix is just 1, nothing more than that. The second is not too complicated. It is exactly the same thing as the parity matrix, but let me write down the one which has little non-trivial structure, and it goes like this. There is a 1, 1, 1. There is a block structure. So this is part of a 4 by 4 labels. So 4 by 4 block is actually just this one. You started from here, use this particular scheme. So 2 by 2 block is just this parity here and parity here, but this extra stuff you added had 1 row of zeros and 1 row of ones. And then you repeated it here again. These are a whole bunch of zeros. And the last one is all ones. So anyway, this is a matrix to go from any occupation label to this Bravyi-Kitaev label. But the point which is here is, if you have the label which can be defined what you call modulo 2, then you can see that these even numbers, you can call the first one as a 0, 0, 2, 4, and 6. They are nothing but 1 on the diagonal and all the off diagonal term equal to 0. So those even numbers are nothing but the occupation label encoding, and the odd ones will have these strings attached to it, starting from that label and going somewhere on the left side. How far you go depend on this parity scheme up to some block level within the block, and the last one goes all the way. So in some sense, even labels have Jordan-Wigner structure and odd labels. And what Bravyi and Kitaev showed, that because this construction is defined recursively, how many recursion steps you need for a given value of n is basically log n, and you need only one new Pauli operator for every level of recursion. That is a crucial point. So the coding ends up that when you want to map this AJ dagger AJ, it is one Pauli matrix for every level of recursion. Nothing more than that. And that is where this weight comes down to order log n. And so this is a nice property to have because it reduces essentially the depth of the calculation. And again, library codes for this mapping is available in Qiskit or something similar. Basically, you just have to define these matrices in a certain scheme, and it works out. And another development after this is not the end of the story. People even found something one little bit better, and I will not give any description of it at all, but say what it is. It's something which is called ternary tree encoding, and weight reduces even more, and the number is log not to the base 2 but base 3. So it's a little bit smaller, and this is the best algorithm known so far. And again, the description can be given. I will skip it, except that the words probably are a little bit interesting. How do you do this? In particular, where does this 3 come from? And that has to do with this ternary tree. So what do you mean by a tree? So there are 3 branches at every location in the tree. It's whatever. Goes like that. That is a mathematical or a pictorial labeling of a graph. What do you mean by a tree? And what are these 3 branches? They are basically mapped to the three Pauli matrices which you are working with, x, y, and z. So at every location you construct a hierarchy, three branches, whether the next one is going to be x or y or z, and you go down some sequence, and then it covers all the possibility in this log 3, how many levels you need to reach a particular stage. And what do you need to do this? That is another label which is well known in various physics nomenclature, something known as the Majorana operators. And the definition is quite simple, but it replaces this A dagger and A, which are in general complex objects, by something which is real by construction, or in this particular case Hermitian by construction. And the easiest way to do that is define two combinations as A plus A dagger and A minus A dagger. And you rewrite everything, whatever went on, in terms of these operators. The reason it works is whatever that Hamiltonian is, ultimately it is Hermitian. We used all this A and A dagger because it described the transitions efficiently, and that went into operators which are not Hermitian, but in principle you can bring it back so that all the Hamiltonian terms are written in terms of Hermitian operators only. And that is what this Majorana basis does. And if you do that, well, you have to code this x, y, z in this particular label. It can be done, and the advantage is that this is still a better description in terms of weight. And as far as I know, the best result available, probably it is also optimal transformation you can do, but then it gives a good solution to this problem, that you can cut down the depth of the calculation. So that is as much as I want to say in this variational quantum eigensolvers. If you want more details, have a look at this review. It is, I will warn you that it is fairly exhaustive. Okay, so you can probably selectively read one section or the other that interests you, but otherwise going through the review will be a course in itself. It's not a small article. And from the next class, I will go on to the subject of how to handle errors. Error correction, there is a separate course, and I'm going to do it, but there are various techniques related to error mitigation, and those are the techniques which I will describe in various forms.